Welcome back to our MECH 1000 video on Blueprint Reading Unit 7. And at the end of the last video, we were in the middle of this practice exercise answering some questions about this special purpose shaft. So let's move along to the next question here that asks for the diameter of the neck. So this is the new concept that was just introduced in the last video. What is a neck? So the neck of this shaft is right here. It's this area that has a reduced diameter. So it goes from a small diameter to an even smaller diameter before jumping up to a larger diameter. So that's the neck right there. We want to know what its diameter is. So it's not given. We're going to have to calculate it. If we look at the diameter to its left, that's 0.468. And the neck is made by cutting a groove, basically, that goes all the way around this cylinder that has a depth of 0.06. So if we take our 0.468, nope, sorry, I wrote that wrong. There we go, 0.468, and we subtract 0.06 is the depth we cut in on one side, but that is also cut down from the other side. We're removing 0.06 from the bottom and the top, so minus 0.06 again, and we should get 0.348 is the diameter of the neck. What is the length of the tapered portion? So this is another new concept that we just learned about in this unit. So here we have a taper, and the taper goes from here over to here. And so we're going to need to know what that length is in order to, well, actually that is what the question is asking. What is the length of the tapered portion? So here we see the length of this portion of the special purpose shaft is 3.50, and that goes out to here. And then if we come down here, this dimension goes back to where this tapered portion begins, and it has a dimension of 1.32. So we just need to take our 3.50 minus 1.32, and that's 2.18 is the answer there. How much tolerance can be accumulated on the length of the tapered portion? So for that calculation we just did, what's the accumulated tolerance? Well, this dimension has 2 decimal places, and so does this one. And a 2 decimal place dimension has a tolerance of plus or minus 0.01. So we accumulated 2 tolerances. 2 times plus or minus 0.01 is equal to plus or minus 0.02. And that's the accumulated tolerance. Okay, so now we get to what is the diameter of the small end of the tapered portion. So we are going to need to remember what this length was of the tapered portion. And if we jump back a couple slides, we can see that that was 2.18. Okay, so we've got 2.18 is the length. And so the way we calculate the diameter at the small end is we take our taper per foot of 2, divide that by 12 in order to find taper per inch. And so that gives us 0.1666 repeating TPI, or taper per inch, The length of the tapered portion we had previously calculated was 2.18. So if we take our 0.1666 repeating and we multiply that by 2.18, we get 0.36333 repeating. And so if we take the diameter at the large end, which is given right here, so that's 1.468, and we subtract from it our 0.363, we get 1.105. And I would say that we want to keep it to just the 3 decimal places because the adjacent diameter was given to 3 decimal places, so we can calculate the diameter at the small end also to the same number of decimal places. Okay, let's move on to the next topic. We've talked quite a bit so far about tolerance, and usually in most of the drawings we've looked at so far, tolerances have been assigned bilaterally plus or minus some amount, like plus or minus 0.1, for example. So the dimension is specified what it should be ideally, and then you add or subtract the tolerance from that amount to find the maximum and minimum allowable sizes. Another way to specify that on drawings is to just put the maximum and minimum amounts on the drawing. Instead of one given dimension, you provide 2 dimensions and you stack them on top of each other. So you might put the maximum dimension on top and the minimum dimension on bottom. And then anything that falls in between those 2 values would be accepted, and anything that falls outside would be rejected. So the total amount of tolerance is the maximum minus the minimum amount. So we don't describe it as a plus or minus amount. So for instance here, if we had these 2 values as our minimum and our maximum limits, we would just take the 0.505 minus 0.500 and get 0.005. So we would say that the tolerance equals 0.005, not plus or minus, just simply 0.005. Now, if we wanted to convert a dimension given as limits into a dimension with a bilateral tolerance, you would need to basically find the middle point or the average of the 2 values, and then add the plus or minus half that tolerance amount. So in this example, we're kind of going the other way around. We're starting with the dimension with a bilateral tolerance, and so we're converting that into limits. So we just add the 0.005 and subtract the 0.005 to find the maximum and minimum amounts. And of course, tolerances are not always bilateral. Sometimes they're unilateral, or just not the same in both directions. So in this example, we have 0.375 plus 0.01, but minus 0. So it could be the minimum is 0.375, but the maximum would be plus 0.01, would be 0.385. Another way tolerances can be expressed is with a single limit, such as a maximum or minimum. So for instance, if we had a dimension like 0.5 max. We're saying that that's the biggest that the dimension can be. It can be smaller than that. Anything smaller than 0.5 would be acceptable, but 0.5 is the biggest it's allowed to be. Or if we had something that was 0.5 minimum, we're saying that it's the smallest it's allowed to be is 0.5. It can be anything bigger than that and be acceptable, but it just can't be anything smaller than 0.5. So this is typically used for corner radii, chamfers, depths of holes, length of threads, etc. Let's answer some questions for this parallel block drawing that is dimensioned with limits. So this is perhaps the first drawing we've looked at that's dimensioned in this way. And we want to show the block thickness with a tolerance that is equal in both directions. So the thickness of the block is this dimension right here. So it is dimensioned with limits. It's saying that this is the biggest it can be. That's the max. And this is the minimum. And if we want to replace that with a single dimension plus or minus a certain amount, like we're used to seeing, what would that be? So this is what I was talking about earlier. We would want to take the average of these two values. So if we add them together and divide by 2 to find their average, we would get 0.9680. And then the maximum amount minus that average is 0.0002. So this is the dimension with a bilateral tolerance. This is what we're used to seeing. So if we took that and we added 0.0002, we would get 0.9682. And if we subtracted 0.0002 from this dimension, we would get 0.9678. So those are two equivalent ways of writing the same information. This is with a dimension and a bilateral tolerance, and this is written with limits. What is the maximum dimension between the centers of the top row of holes and the bottom row? So when it comes to answering questions about maximum and minimum values, we have to be somewhat careful. In this question, it's asking about the dimension from here to here, from the top row of holes to the bottom. Now this question's fairly straightforward. We want to know the maximum dimension that this can be. And we're adding two dimensions together. So it makes sense that the maximum dimension would result from taking the maximum that that dimension can be and the maximum that that dimension can be, add those two values together, and we should get 1.5004. So that makes sense. That's straightforward. What about this next question? What is the maximum dimension between the bottom row and the bottom of the block? So we want to know what is the maximum that this dimension can be. So some people's instinct might be to use the maximum value here and the maximum value here, but that would be incorrect. We want to maximize this dimension. So that means making this dimension as big as it can be, but then subtracting from it the least that this other dimension can be. And so if we take the 1.4842 minus 0.7498, that will give us the maximum dimension of 0.7344. And it looks like I'm about out of time, so we're going to have to wrap this one up in the next video.